Good morning. My name is Sharon from CSC AIML Section C. So today my topic is relation crystal structure with breakdown of polyethylene thin film. The ancient enemy crystal structure and polyethylene thin film breakdown. So let us start an introduction with this. So, what is a polyethylene? Polyethylene is a polymer widely used as an insulating material in electrical and electronic applications. Its electrical performance depends largely on its crystal structure and morphology. So, introduction, the ubiquity and vulnerability of polyethylene films. Polyethylene PE is a cheap, flexible, and product at a massive scale. Thin films, that is, range from 10 to 200 micromillimeters, are everywhere, but their thinness and microstructure make them vulnerable to environmental, mechanical, and chemical breakdown. Understanding polyethylene. A brief chemical overview. So here is a structure that we use in chemistry, formula structure. You can see it in the image. And coming to the basic chemistry, PE is a linear hydrocarbon polymer, repeating CH2 chains, chain length, branching, and tacticity, control, packing, and crystallinity types HDPE, high density, low branching, and LDPE, branched, show very different film behaviors. The crystal structure of polyethylene. Order amidst chaos. PE films are semi-crystalline, crystalline order regions embedded in an amorphous matrix. Crystals form spiralities radiating fibrils that meet at centers, producing mechanical anisotropy and diffusion pathways. The role of crystallinity in material properties. Crystallinity, that means stiffiness. Higher fraction of crystalline regions increase modules and tensile strength, but reduces elongation at break. Amorphous region, toughness and ductility. Amorphous regions absorb energy and enable plastic deformation. They govern impact and tear resistance. Transport and aging. Diffusion of oxygen, water, and radicals is faster through amorphous zones, making them hotspots for chemical degradation. So, polythene consists of both a crystalline and amorphous region. The crystalline region have tightly packed molecular chain, which make the material stronger and more resistant to electrical breakdown. In contrast, the amorphous region contain loosely packed chains, which move more free volume, where change carriers can move more easily. When a high electric field is applied, the breakdown usually starts in the amorphous region because they have lower density and weak molecular bonding. However, the overall breakdown strength of polythene increases with higher crystallinity as the dense crystalline zone restrict change movement and reduce defects the case breakdown. Degradation mechanisms, how polythene film fails. Photooxidation is one of the point. UV generates radicals and chain scission and cross-linking. So this will break down and cross-links the chain that makes the polyethylene film fail. And second one is thermo-oxidation. Evaluated temperature accelerates same radical chemistry. So here the temperature will be increased. So due to that the polythene film fails. And mechanical fatigue, repeated chain strain causes lameable decohesion and crack growth. Chemical attack and stress cracking. Solvents or detergents swell amorphous regions. Combined stress causes environmental stress cracking. Linking crystal structure to degradation pathways. Key links. Radial formation localizes in amorphous region. Chain cessation there reduces entanglement and enables brittle failures. Crystalline lamellae can inhibit crack initialization, but once microvoids form a lamel amorphous interfaces, cracks propagate rapidly. Spiralized size matters. Large spiralites create weak interboundaries that accelerate tear growth. Orientation, biaxial and machine direction orientation aligns chains, raising strength but increasing anisotropic uh, crack paths. Case study. Analyzing breakdown in diverse polythene films. Microscopy. Polarized optical and semi-reviewable spirulate size, lamellar thickness and void formation after aging. Thermal analysis. DSC qualifies crystallinity percent and melting behavior. Predictive and mechanical performance after heating cycles. Chemical assays, FTIR and chemiluminum senses track oxidation process radical activity to map degradation kinetics. Mitigation strategies designing for enhanced durability, UV uh, stabilization, add UV absorbers or HALS to intercept radical and slow photo oxidation, optimize crystallinity, tune cooling rates and draw ratios to produce fine lamellae and controlled spiralized sizes. Blend and barrier layers. Use co-extended barrier layers or polymer blends to reduce permeation and chemical ingress. Antioxidants and additives. Primary and secondary antioxidants protect shines for a lifetime. And polyethylene that means crystalline regions are tightly packed and fewer defects, offering high resistance to electrical breakdown. Future directions, novel materials and structural engineering. Functional coatings, nanocoatings that block UV and chemical attack without adding thickness. Chain architecture engineering, Tailor branching and block copolymers to balance toughness with barrier performance. Process directed microstructure, controlled cooling, inline annealing, and shear fields to create desirable lamellar morphologies. Sustainable design. Bio-based polymers are recyclable strategies that maintain performance while reducing environmental impact. Takeaway. Understanding engineering crystal structure at a micro and nanoscale is the most efficient role to long-lasting polythene thin films. So from this, we have got that polyethylene has both crystalline and amorphous. That means order and disorder regions. And crystalline regions are tightly packed and have fewer defects, offering high resistance to electrical breakdown. And amorphous regions are loosely packed and contain free spaces where charge carriers can move easily, making them weak points for breakdown. And higher crystallinity increases dielectric strength because it reduces charge mobility and traps impurities. Temperature and processing models affect crystallinity, and higher temperature or faster cooling can reduce crystal formation. Thin films with uniform and fine crystal structures show better electrical performance and slower aging under stress. Breakdown often starts at the boundaries between crystalline and amorphous region where structural irregularities exist. And the conclusion, in summary, the crystal structure directly affects the electrical breakdown strength of polythene thin films. Greater crystallinity and uniform structure improves insulation and durability. Whole amorphous or irregular regions lower breakdown resistance. Right, thank you.